The point of this lecture state change calculations for one phase was to try and to bridge the gap between you given CP data and for an ideal gas at a certain pressure, but then how do you work that out for a real gas? And how do you use the CP data for an ideal gas for a real gas? And the point was to like bridge that gap. But before we bridge that gap, we need to find out more about CP. And then we just do this for one phase, but eventually apply this to other phases. So the thing here was to just show you that you have pressure, volume, and temperature in 3D, right? And then you know your PT graphs or your PV graphs, they are actually 2D projections of the surface. And for pure substance, you normally go, okay, you evaluate a PT or PV space, but I want you to understand that they come from projections from the surface, and P and V and T are all related. We'll look at PT for this lecture, and when you look at heat engines, you'll look at PV because that's work. If you recall this from your second year, this is quite useful because we're working in the PT space, but you have solid, liquid, gas, but we're just considering for a gas for this lecture. And then for the other lecture, you'll consider from a solid to a gas. But for now, we're just dealing with a gas and understanding that when we work in this area, when your pressure is in atmospheric units and temperature is degrees Celsius, for this graph, you have a gas here, a solid here, and liquid here, and maybe P atmospheres down here. But this is specific for specific components, right? So we went on to look at CP, and you're normally giving CP. You always normally look at your textbooks. You're normally giving CP data for an ideal gas at 1 atmosphere. You're okay. So let us understand CP a bit more. And for an equation of state, also given PV equals nRT. And then now, what was the point of lecture 4 was to derive equations like this so that we can use CP data, an equation of states, to represent volume, temperature, and partially differentiate that equation state so that we can eventually calculate DH or delta H's or states of change. Right. So the point of this section was to show that the ideal gas is not a function of the CP is not a function of pressure, but that also delta and that delta U is not a function of pressure, but delta S is for an ideal gas. So you could consider two paths, and yeah, so using this equation here, you evaluate this equation for each path. So you'd evaluate it for A, and then you'd evaluate it for when pressure is constant, and then when T is constant, and then you eventually get to an equation for the here. So this is when pressure is constant, and then when this is T is constant. So this was evaluated where dP was 0, and this was evaluated, your DH term, where dt was 0, and it eventually whittled down to this two equations. But then in this equation, you see you have dV and dt. So what you need to do is you actually need to substitute in for V. But you know V because I told you it's an ideal gas. So you can express this V and this T and this dV dt using your ideal gas expression of state. And then you can substitute that into the equation for path A. What's also important to note where you evaluate it at is to have cognizance of if pressure is constant, what pressure is it constant at. So in this case, it was constant at P1 for this DH term. And then for this DH term, what was constant? Your T2 was constant. So you evaluate this term at T2. And the point why you can't do this, because H is additive and it's extensive, but then H equals H1 plus H2, and H1 over here, H1 to that point, and H2 to that point, it's a DH, and that's how you can evaluate the function and the paths on the PT graph. So you eventually can find for path A that DH delta H equals Cp dt, and for path B you also find delta H equals Cp dt. And what that's highlighting to you is to show that Cp is not a function of pressure, because why? Delta H, your delta H's are state functions, they will always be the same. That means that your Cp are also the same in this case, and it doesn't matter if you evaluate at pressure 1 or at pressure 2, you'll get to the same dH. Right, so the next part, before even moving on to the next part, it was to show that what would help you even more. So for an ideal gas, you know Cp is not a function of pressure, but also what you can show by using your thermodynamic equations, dH equals Cp dt plus RT over P minus TR over P dP. If you substitute, so this is from, this is dH from an ideal gas, you'll find that dH equals Cp dt. So it's showing you that for an ideal gas, it's not a strong function of pressure, because those terms cancel out. Where did this come from? This came from your equation dH equals Cp dt plus V minus T partial derivative V minus T. So this is from your equation sheet dP. So for real gas, the enthalpy is a function of temperature and it's a function of pressure. But for an ideal gas, it's only a function of temperature, your enthalpy. And also what's more, if you look at your ds equals Cp over T dt minus dV by dt Tp dP, you'll actually still find for an ideal gas, your entropy is still a function of temperature and pressure when you substitute in for your equation of state. Equation state for an ideal gas. So yeah, your entropy is still a function of temperature and pressure. What about internal energy? Well, that's for you to find out. I want you to prove if du, so you know on your equation sheet, du equals Cv plus dt, T dP by dt Tv minus P dV. Is U a function of temperature and volume? And for your other thermodynamic equation for entropy with respect to Cv, is entropy a function of temperature and pressure for an ideal gas? So evaluate for an ideal gas. And what you'll find actually is that U is only a function of T for an ideal gas, but S is a function of T and V for an ideal gas. That's what you will eventually find. And you should do the little sheet of paper in class to check out for solids and liquids, how pressure changes for liquids and solids, for entropy, internal energy, and enthalpy. But yeah, that was the point of this, to show if you're given Cp data for an ideal gas, what do you know? You know that Cp is not a function of pressure, but also for an ideal gas, your enthalpy is not a strong function of pressure, but for entropy, your ideal gas is a strong function of temperature and pressure.